Well, good evening, ladies and gentlemen, students. This is Arthur Johnson speaking, and this is April 20th, 2020. I hope you're well and settled comfortably in front of your screen so that we can have this first part of tonight's class, my presentation on exoplanets and ways of finding them. So what does the term mean? Exo comes from exotic or outside or otherworldly. Exoplanets are understood to mean planets that go around some star other than the star in our own solar system. So until fairly recently, we only speculated that they could exist. You cannot take even the biggest telescope on Earth and point it at even the nearest star and easily see planets going around it. It turns out to be a pretty daunting task. But for generations and generations, astronomers, and everybody else too, looking at the nighttime sky must have been both dazzled by its beauty and perhaps have allowed their minds to wander and their imaginations to go crazy and ask the question, are we alone orbiting our sun, or are those other suns that we see in the sky in the Milky Way themselves possessing systems of planets? It's a worthy question, and in our own time we have been able to come up with the answer for sure. Exoplanets are out there, and there are a lot of them. I'll tell you how many as we get a little further on. Well, back when the Earth was considered the center of the universe, these debates were not widely entertained. And one fellow who did entertain them was the philosopher Giordano Bruno, who wrote that he believed that there were an infinity of worlds of the same kind as our own. This did not go over well with the church authorities, and he was, for his trouble, burned at the stake in February of the year 1600. Not a very wise guy to advocate something like this in a time when the religious authorities insisted that Earth was unique and everything was all about us. Well, if we go forward just a bit, we come to this individual, Sir Isaac Newton, who is a towering figure in the history of science and human thought. He was the inventor of a kind of telescope. He discovered the universal theory of gravitation. He invented the calculus, one of the great towering figures of Western thought. And Newton thought about planets and how they orbited the sun. And in particular, if you'll bear with me here, here's just a little graphic that shows the universal theory of gravitation that Newton articulated in his book Principia. And he's basically said that every object in the universe exerts an attractive force on every other object in the universe. This force is the product of their masses divided by the square of the distance in between them. Well, what does that mean in practical terms? Let's consider Jupiter and the Sun. We say that Jupiter is in orbit about the Sun, but it is equally true that the Sun is in orbit about, now stay with me here, the barycenter, the actual common center of mass between them. The barycenter of the Sun and Jupiter lies just above the surface of the Sun. So if you were to watch very carefully, you would see that, yes, Jupiter appears to be going around the Sun, but it is more strictly true that the planet is going around the barycenter, as is the Sun. So once every 12 years, as Jupiter completes an orbit, the Sun itself completes a very tiny orbit around that center of mass of the system. Well, this is going to be really important to us as we talk about how 20th and 21st century astronomers went about trying to detect other planets. The first detection that was unambiguous and clear was made in 1992, just about 30 years ago nearly, when planets were found orbiting a very exotic kind of star called a pulsar, actually a collapsed star that emits pulses of radiation. A few years later, in 1995, a planet was found orbiting a less exotic type of star in the constellation of Pegasus. And this star completed an orbit in just 4.2 days. Now, compare that with the closest planet to our own sun, Mercury, which requires 88 days. So the planet that these two scientists found was really almost touching the surface of its star, and we regard it today as the archetype for what's called the hot Jupiter class of exoplanets. More about that a little bit later on. But those two astronomers were just last year in 2019 the recipients of the Nobel Prize in Physics. Well, since 1992, we have found a lot of planets. I'll give you the actual number when I am handed the envelope here at the conclusion of our talk. But there are about 5 ways now recognized for finding planets. And if you look at the fine print, you will see that the first 4 are fairly often used. The last one listed here, astrometry, has been used in only one successful case. So we're going to find actually that the biggest producer of results is the transit method, but I'm going to talk us through all of them at least briefly. Here we go. So we start with the radial velocity method, okay? Radial velocity is a term astronomers use to talk about whether a star is moving toward the Earth or away from the Earth. Radial velocity. It's moving toward us or away from us. Now, when I start this animation, we're going to see our little hypothetical planet and its parent star in their orbit. And just as promised, you will see that they are orbiting the common center of mass. Now, second method, and the one that has produced more confirmed planets than any other, it's the transit method. And I'll talk about what that amounts to. We start here with let's take another example. Here is a pair of stars, and we're going to show that one of them has a larger planet orbiting it. And the one on the right has a smaller. So if you were watching the light curve with your telescope, you can't see the planets directly, but you're tracking the brightness. Here's the astrometry method, tiny movements. This one's only been used in one case, and it had to be a star system that was really, really close. But
again, bearing in mind what Newton's law tells us, we see that the two objects are moved. Now here's direct imaging. A star is so bright that we cannot possibly see its planets, but if we insert a metal disc into the telescope in just the right way, that metal disc can cover for us the main blinding part of the star and allow us to see one or more planets when that. The last one I'll mention is gravitation.
lensing. You'll remember that I spoke on our eclipse lecture about astronomers observing the light of a distant star passing very near the edge of the sun to going to where we are now. And again, that number is coming up soon. This work cannot really be done from Earth very satisfactorily because the Earth's atmosphere causes stars to twinkle. Their positions seem to shift very slightly. It's very difficult to get extremely clear and precise views looking through the turbulent atmosphere of Earth. But in the 21st century, we have had two telescopes that were launched by NASA on purpose to look for evidence of extraterrestrial or extrasolar planets. The first was the Kepler Space Telescope, which had a roughly 9-year mission. It was launched in March of 2009, and it was decommissioned in November of 2018. Its mission was to search for exoplanets that might resemble Earth. Well, it found lots and lots of them, but just in the last 2 years, since 2018, got the century wrong there, NASA has put up another project called TESS, which is really the next generation. It has better technology and can detect smaller planets than those that were found by the Kepler. It was launched in April 2 years ago, just almost exactly 2 years to this day. Started planet searching July of that year, and by September it had found its first candidate. It was trying in particular to look for smaller, more Earth-sized planets. The ones found by the earlier Kepler telescope tended to be what we call hot Jupiters, really, really massive planets that were in some cases almost as big as their star themselves. In some cases, we debated whether they were stars. We call those brown dwarfs. The expectation for TESS, which is mostly finished with its mission, but it is ongoing, that thousands of planets smaller than Neptune will be discovered, and at least some dozens of them may be down to the size of our own planet, the Earth. All right, this is almost the latest data from the website. Right now, earlier in this month anyway, there have been found 4,241 exoplanets confirmed, with several thousand others suspected but awaiting confirmation. So, having talked about that, we might ask, all right, well, what do you need exactly to have a reasonable candidate for a planet that could bear life? The Goldilocks Zone is a lovely term, and of course, if you remember the fairy tale, Goldilocks and the Three Bears, she was after things that the porridge could not be too hot, could not be too cold, it would be just right. And that concept is used today. We use a somewhat less fairy tale term, the CHZ, or the Circumstellar Habitable Zone, which is defined as that range of orbits around any star, a given star, where the planetary surface could conceivably support liquid water. Why that? Why is that important? Well, biologists are reasonably certain that any extraterrestrial life is likely to be carbon-based, as is our life form, and life on Earth, which is the only example we know for sure, thrives in a chemistry where liquid water is present. That's not to say other biology couldn't exist, but anyway, this is where we're looking for starters. And as it turns out, among those 4,000 plus exoplanets that have been thus far discovered, there are quite a number that are in the conceivably habitable zones around their planet. You can see Earth there at about the upper 1/3 of the diagram, and any number, well, not any number, but a dozen or more other planets that have been discovered around other stars. Pay particular attention to Proxima Centauri. These are the nearest potentially habitable exoplanets that have been found thus far. And at the extreme upper left, and these are ranked from the distance of closest to us at upper left to getting further and further away, it turns out that the very nearest star system to us, that's the Alpha Centauri system, has a planet that is reasonably comparable in size to the Earth. It's a little more massive, and it does definitely lie within the habitable zone. Now, that's not to allow us to jump yet to a conclusion, because there are a couple of problems. Proxima Centauri b is something like 20 times closer to its own star than the Earth is to the Sun, and that produces an annual revolution around the parent star of just 11.2 days. Okay, compared that with 88 days for our Mercury. So it's really whipping around the Sun fast. The solar wind pressure, it's been calculated to be something like 2,000 times greater at this little planet than what we have on Earth. And even more discouraging is the fact that Proxima Centauri is known to be a flare star, which has extreme propensity for violent eruptions that could blast any potential life with X radiation. So it's not a done deal for sure. But remember, we've only been at this enterprise since 1992. Only in the last few years have we really had the kind of technology get into place that can begin to do the job of assaying potential planets. We're finding the planets, but how we would proceed to detect life, well, that's a subject perhaps for another time. But I'll close with a little artist's rendering of what Proxima Centauri b might look like. So anyway, it was just a week ago that one of you was kind enough to suggest a topic for a lecture, and I did my best to get something together in just a week's time. So I hope you've enjoyed it, and we'll end the slideshow here, and I will be very happy to entertain your questions. Thank you. And the star was seemingly moved out of its normal position during that solar eclipse. This is a general relativity method, and it has been used to detect some hundreds of planets. So we have gone from not knowing until 1992 if any exoplanets really exist. Contrast has been removed. So this is direct imaging. You actually get to photograph or see the planet. Not terribly many planetary systems are close enough for this to be true, but it has been used. About their common center of mass. And although the planet is too dim for us to see, we can track the position of the parent star, and over the course of one of its orbits, we see that it makes a tiny circle. And so this is one additional tool that astronomers have used. Now watch the graphs. Suddenly the brightness drops way down in the case of the larger star, and drops down to a lesser extent when the smaller planet transits the face of its parent object. Okay, the transit method, and this one has been to date used to detect the existence of more than 3,000 exoplanets. View of a hypothetical solar system seen from above. Now we turn it edge on, and if we watch the light curve of the main star, we can't see the planet, but we see that the light from the planet is dimmed, and then it brightens back up when the planet gets out of the way. Here comes another one. Watch the light curve. And this is the productive method that various space telescopes have used over and over again. Thousands and thousands of planets have been detected using the so-called transit method. Let's turn it edge on so that we see what the star is doing. Look at the wavelengths of light shown below. Some of the time the star is moving towards Earth and gives us a blue shift, and later in the orbital period it's moving away from us, giving us a red shift. So with spectrometers, astronomers look at stars in this situation, and when they see one moving alternatively toward us and away from us and very regularly, then they can calculate the existence of a planet.